So let's start. So the first sort of speaker at the regular time in this seminar for this year is Jenya Sapir. So she was a PhD student of Mirzakhani in Stanford. She graduated last semester, and now she's a new Duke assistant professor here. And she's going to tell us something about counting non-simple closed curves and surfaces.
There we go. Okay. Hey everyone. Thanks for having me as the first Tuesday speaker. So I'm going to, the slide that's gone and vanished is, I'm going to talk about counting non-simple closed curves on surfaces, so I may as well do some notation. S is going to be a surface, negatively curved, usually hyperbolic. If it has boundary, it'll be geodesic boundary. And then I'll be talking in particular about pairs of pants, so they're important, right? We're talking about closed geodesics. They're non-simple. The set of closed geodesics is denoted by GC, right? But they will be primitive, right? They can't wrap around themselves more than once. Okay. And then just quick background. Geodesics are unique in their free homotopy class, right? The picture is that, if we have like the cylinders look sort of curvy like this, there's just one shortest guy. And so counting geodesics is like counting free homotopy classes of curves. Okay, so I'm going to go into the history first of some curve counting problems. So let's talk about asymptotic bounds. So what is the question? So let GC of L be the set of geodesics, closed geodesics of length at most L, right? And then there's this famous theorem of Margulis that says that if S is a surface of finite volume, then, but not necessarily hyperbolic, right? Then the number of closed curves of length at most L is exponential in L. With this constant delta, that's the topological entropy of geodesic flow. And, okay, so notation real quick, little twiddle means asymptotic, right? The limit goes to 1. And note, when S is hyperbolic, delta is just 1. And actually, so even when S doesn't have finite volume, but let's say it's geometrically finite, so it's Jesus or something, then there's similar results. This is similar asymptotic.
So the middle sign means here that the ratio between the two quantities goes to 1?
Yes, so on the nose, yeah.
Negatively curved? Or
yes, yeah, assuming that negatively curved, that's very important. So it could be variable curvature bounded away from 0. Okay, and because I like to have pictures, there's an aside to this, which sort of shows you why you might believe a exponential growth, right? So I'm not going to go into detail, and in fact, this problem isn't actually, so the proof isn't simpler. But so here's a picture. If I have a surface S, right, and I have some point, I can look at geodesic arcs that go from this point back to itself, right? And then I can go up to universal cover. And the set of such things is just the set of all lifts. This is X. The set of all lifts of, this point X is equivalent, right? Because this arc goes to like some little guy here. So the set of all sort of these arcs of length at most L is like the set of all these lattice points in a ball of radius L upstairs. And so it's not actually trivial to prove. It's a theorem due to Huber, I believe, but that the growth of these is exponential. But if you squint and just ignore any troubling issues that might come to mind, then yay, exponential growth. Okay. So that's length. Great. So now I'm going to talk about counting with respect to length and self-intersection number. Right, so we're going to let GCLK be the set of geodesics of length at most L and most K self-intersections. Here's a picture, right? The guy on the closed surface has 4 self-intersections, so he's in GCL4. Of course, he's also in GCL100. Right, it's not equality, it's inequality. And so the question is, if you let K be a function of length, right, can we find some sort of asymptotic growth for GCLK as L goes to infinity? Right? So not very much is known about this. right? When L is 0, we can talk about the set of simple closed curves, closed geodesics on the surface. So, the picture on the right is just to show that simple closed curves are actually quite complicated, right? They go and they spiral around and they do all this crazy stuff, right? So, there are actually there are cannibally many of them. But, okay, so then there's a theorem of Mariam's that says that the asymptotic growth of the number of simple closed curves of length the most L grows like L to the 6g minus 6 plus 2n times some constant depending on the geometry of S. What is this 6g minus 6 plus 2n? So that's the dimension of tabular space, or equivalently the dimension of the set of measured laminations. Okay, and somehow this lattice point picture repeats itself here, right? There's this idea that in the set of measured laminations, simple closed curves are like lattice points, and you can count them. So that's like the cartoon. Okay.
Is it obvious that we should have a polynomial upper bound? Here is an intersection of like one or two self-intersections.
So yeah, well, obvious. I'm not sure. So for simple guys, this lattice point thing really gives you like an easy, sort of like an upper bound, because the if you look at the set of measured laminations and you put charts coming from train tracks on them, the integer sort of coordinate guys are simple multi-curves. And so the number of points, like lattice points in a ball of radius r somehow grows like the dimension of the space, which is this polynomial. For non-simple guys, yeah,
it should be something, but okay.
It's trickier. Yeah, so I'll get to, there's a way of showing that it should be roughly polynomial actually, but it requires a bit of stuff. So, okay, the only other asymptotic bound that's, okay, right. G is a genus of S and N is a number of functors. I guess that's probably obvious, but let's write that. Okay, the only other asymptotic bound that's known is for one self-intersection, right? There's a picture, right? And it's a theorem of Rivin, which sort of follows basically from the simple closed curve case, that this is also it grows like the same polynomial in L.
The degree of this polynomial is the same? No,
yes, it's the same. It's the same. Yeah, so in fact, you do expect the same, yeah. Well, so no, you put a metric on it. And the metric determines this constant. Right, because if the surface I put like a really small simple closed curve on it, right, then the number of these guys is going to be sort of smaller.
If you should change the metric, I mean the constant is going to...
Changes, yeah.
Right?
What's up?
Should no? Stay in a bounded...
Not necessarily, right? Because if you start pinching your curve down, then your surface starts looking like two smaller genus surfaces, right? So it should start, there should be something else going on. I don't think so. Is it true?
I think the function might be bounded on moduli space.
Oh, maybe. Oh, okay. Oh, it is.
I think it is, right? I mean,
oh, is it? Okay.
For multi-curves,
yeah, but nevertheless, I mean, so once you get here, it's still the same, probably it just means that the ratio goes to 1,
yes.
Right? Which is a more precise statement than...
That's right, yeah. Yeah, so that's right, even if the constant is bounded, this actually says that the ratio goes to this on the nose, like it goes to this on the nose.
If you're counting multi-curves less than or equal to something,
right?
Integral multi-curves, then it's L this 6g minus 6
right.
again, and there the constant is bounded on moduli space, and almost everywhere the constant is 1.
Right.
Or normal 1. It's the same thing.
But then you have to figure out which proportion of those are simple.
That's right.
Right, and that's where the metric.
I'm not talking about okay. I'm saying multi-curves.
Yeah, that's right. Yeah.
Integral multi-curves. If you count them, then that constant, you again get the same degree, but the constant is constant almost everywhere on moduli space.
Right.
So,
yeah.
And this is a very recent result, right?
Yes. Mariam, but it's written down in a paper of David Dumas, who attributed.
No, I mean
this one, it's around the same something. Yeah. So probably just before I started grad school. So yeah. That's how I'm gonna tell time. Okay.
So it's classical.
It's before I was born.
2009.
Okay. Anyway, so moving on. Right. So that, like I said, that's basically all that's known for asymptotics, right? So what bounds can you get? So let's formulate a question first, right? Like I said, no asymptotics for an arbitrary function. So the question is, what are the best bounds we can get for the size of G CLK, fixing an L and K, right? But the bounds should be in these two parameters. Okay, so obviously there's something stupid you can do. All right, the simple closed curves live inside of the guys of length K, which live inside of everyone. So, okay, we have some sort of horribly big range. But we want to do a little bit better than that. So let's fix K and see what we can do. So there's, as a consequence of a theorem of Athreya, Befedov, Eskin, Mirzakhani, and then you use a result of Asmagine and some classical results. You can show that roughly GCLK grows like this f of k times the L to the correct, so times the correct polynomial bound, where f of k is the number of mapping class group orbits of the set of geodesics with at most k self-intersections. So the mapping class group acts on the set of geodesics, right? And it preserves intersection number. And in fact, the number of orbits for a fixed upper bound intersection number are finite, right? You can think about like the number of orbits for simple closed curves are finite, right? That depends on the topological type, the surface you get when you cut out, cut by the simple closed curve, and you get something similar. But, right, this f of k is not known.
So it's not known how f of k grows, this case?
No, it's not.
And this should be like GC of like infinity k, right? I mean, or it doesn't really make sense to talk about.
Yeah. So I mean, as L gets bigger, you'll eventually exhaust all the things, right? So it's kind of, just GC of infinity k looks weird. So it's GCLK. GC star k, I guess, yeah. Okay, so there's that, but there's not an explicit dependence on k here. So that's sort of what I'm working on. Oh yeah, so this little curvy equal sign just means up to a constant multiple, inequality up to a constant multiple, and whoops, there is no c. I don't know why. Oh no, the c is there. There it is. Yeah, okay. Okay. So what happens next? Like I said, f of k is finite, but not known in general. Okay, so what have we got? In summary, for an arbitrary k, we have growth like exponential. For a k fixed, we have growth like this polynomial, right? So the problem is to sort of extrapolate between these two very different growth rates. So we want to do something like that. Okay, so before we can talk about this, what should be sort of, what should the answer be? Right, so let's talk about the independence of the self-intersection of a closed geodesic with its length. So there's a theorem, Buter-Lally, that says if you choose at random, the geodesics of length the most L, take the sequence as L goes to infinity, then almost surely so the geodesic you chose at random of length the most L is probably going to have length L, right? Because it grows exponentially. So almost surely the self-intersection number grows like this kappa times length squared, where kappa depends on the geometry, on the metric you chose. Okay? And then for any geodesic you choose, its self-intersection number is at most its length squared times some other constant lambda. Okay? So roughly speaking, almost all geodesics have maximal self-intersection number, which is length squared. Okay. So somehow this needs to show up. Okay, so whenever we see, you can't see that.
I forget, is Bonhoeffer's estimate similar? For the random geodesic in terms of taking a random tangent vector?
I think he just gets bounds. I think.
Remember, there is a formula there, right?
For the self-intersection number?
Yeah.
No, I think for a random geodesic, that's Lally again, right? The number of...
No. But Bonhoeffer already has, in his papers on geodesic terms, I remember there is something about what happens to the self-intersection number if you start.
I think.
I don't remember.
Yeah, because, after you projectivize correctly...
Oh, that's right, yeah, because... So if you have some sequence that converges, of these guys that converges to the metric. That's true, yeah.
That's actually also correct.
Okay. So what you can't see there is that you should think of intersection numbers. I'm not sure there are going to be that many more slides. I'm afraid it's just going to... Oh, it doesn't help. The projector gods are against us. It's okay. You can see the top half. The point is the intersection number you should think of as length squared. It's like the cartoon. Okay. So what I'm going to talk about today is how you might bound the number of geodesics of length the most L with the most k-self intersections for arbitrary L and K, and get explicit sort of formulas in both variables. So I'm going to give you an idea for an arbitrary surface S, where things get a little bit technical, so I'm not going to go into that. And then I'm going to show sort of the example of a pair of pants, because you can do something slightly different on a pair of pants, because it's just a simpler surface, and to sort of give you an idea for how things work. Okay, so on a surface. So I'm about to put up a formula that's not the prettiest. So just, if it's too ugly, just think L as root K. So here's the idea. So let's do it for a closed genus G surface. We get that the number of closed geodesics is at most, so you get an upper bound. There's the minimum of some constant depending on your metric x times e to the L. So that's just the Margulis result. And then there's something else. So there's this exponential that's roughly L to the root K. OK. So when you put L in for root K down here, it's not the best. It's L to L rather than e to the L. But it's something similar. Right? And
this is true not just in constant negative curvature. This is variable also?
Yes. Yeah, the technique works. I'll explain why. So
I'm confused. The term below seems to be bigger than the term above.
Right? For some, okay, yeah. Well, so it flips when k is like L squared over log squared L.
But I mean, here this is L and K are arbitrary, right? Oh,
yes. So you fix them.
Okay. So when K is small, then
it's constant. This gives you polynomial small.
Okay.
No. Yeah, CG is not the best constant, but yeah. Okay, so quick corollary, right? So you see that when you put in K of L as something that grows slower, then okay, you want length squared. You actually get that for a pair of pants, but really, so here it's length squared over log squared L. Then the number of geodesics with most k self-intersections is exponentially fewer than all of them for a given length. So that's already nice, right? That's sort of somehow quantifying. You know there's supposed to be fewer when your intersection number isn't length squared. That's sort of quantifying how many fewer. OK, so let me give you an idea for how to do something like this. So suppose for each geodesic, we could map it somehow, maybe hopefully injectively, to some sequence of simpler curves. Like alpha 1 through alpha n are in some simpler set of curves A. This is all going to be very hand-wavy, and then hopefully I'll give some more details. And suppose we can count, so something of L is just a number of things of length at most L. Suppose we can count how many of these simpler guys there are of length at most L. Then all we really need to know is figure out what is the dependence of the length of the sequence on length of intersection number of your original curve. OK? And then you just do something stupid and say, OK, then it's just the number. Oh, that should be A of L. Right, then it's the number of these simpler guys at length at most L raised to this n of Lk. So somehow you could sort of build a gamma by choosing alpha 1 through alpha n randomly, and then the number of them you're allowed to choose is this NLK.
Each one is a concatenation of a bunch of the smaller ones, and so
something like that, yeah. I mean, not any concatenation necessarily works, but OK, so it's something like this. So let me sort of explain how this works for an arbitrary surface. So what we do is instead of working with a negatively curved metric, we take our closed guy and we squish it. We put a flat metric with one singular point. OK? And what that does is, we have our geodesic gamma, which turns into geodesic on this new metric, and it vacuums everything up to that singular point. and it makes it this bouquet of saddle connections. So maybe you want, just to say, okay, gamma turns into this concatenation of saddle connections. That doesn't work. The problem is that you can even have a simple closed curve that has a ton of saddle connections in it, right? So that's no good. But okay, so there's a workaround. Instead, you take these guys, instead of being these little simple closed curves, you take them to be simple arcs, where it's defined in some way. So this picture is just, we have some geodesic gamma, that's some saddle connections, and then we sort of look at it maybe in a nearby negatively curved metric. It's like nearby enough that like you can actually see the self-intersections of this guy, and you can break it up into simple arcs like that. We can sort of see what a simple arc is, right? So maybe, I keep going, and then when I get to here, that's one simple arc. Okay, and that turns out to be enough.
So somehow you're choosing metrics, so all the self-intersections are concentrated in that gray region, or there might be other ones?
There could be other ones, because saddle connections can intersect each other. Yeah, so they're not. The gray region is just sort of, if you allow the saddle connections to sort of wiggle a little bit, then you can actually see the intersections of the curve. Yeah. So it turns out that counting the number of these simple arcs of length the most L isn't so bad. This is just a combinatorial argument. It grows like a polynomial in L. And then,
what are the endpoints of these arcs?
So the endpoints of the arcs are this. So the simple arcs are sort of concatenations of saddle connections that when you do this sort of nearby thing in some suitably well-defined way, you get something simple, or you can get something simple. Yeah, so in some way, this is just counting how many different simple arcs you can put down and then put them together into something simple. So that's not so bad. And then you want to count, how many of these simple arcs can you put down, right? You find this bound in terms of length and self-intersection number. And so the way that you get this bound is actually very similar for what you do on a pair of pants. So instead of going into this part, I'm just going to switch gears completely, go to a pair of pants, and we're just going to look at the bounds there. Okay? This is the last we're going to see of surfaces. Okay, so illustration on a pair of pants. So pairs of pants are nicer because, whereas here we had countably many simple closed curves, like these saddle connections, on a pair of pants are just 3 of them. So somehow things are going to be simpler. So there's actually a different theorem which is slightly better bounds you can get on a pair of pants, which I'm not going to state, but the construction is a little bit different. So what do? Instead of taking a flat metric, so this is for a hyperbolic pair of pants. We're going to take our geodesic gamma on the pair of pants, and somehow we're going to project it. We're going to tighten it up so it follows, so it sort of basically just follows the boundaries with just 3 possible paths between them. Or rather 6 because you need orientation. But so you send gamma to this word v1, vn, where these vi's are just sort of half twists, powers of half twists around the boundaries. Okay? And then, so notice that the sequence actually determines the curve, a curve that's homotopic to gamma. Because here I'm going, I go up, let's say I do 3, I think that's 3 half twists, and then the next one starts here. There's only one way I can really go to join them. Right, so the sequence of powers of half twists around the boundaries determine a curve homotopic to gamma. And so, in fact, this map is 1-to-1. So to get an upper bound on the number of geodesics, you just have to get an upper bound on a number of these words.
What do you mean 1-to-1? What about cyclic limitation?
Oh, sorry. Yeah. So it should be a cyclic word. Yeah. Thank you. Okay. So if you have a cyclic word, then it's 1-to-1. Yeah, you'll notice here, so these 2 curves might look a little different. This guy here that sort of goes and twists around, what I've done is I've taken him and I've pulled him sort of tight to the other two boundaries. But in fact, this sort of represents how curves on a pair of pants can't really do that much but wind around boundary components. Okay, so like I said, there are only 3 boundary curves. So somehow up to some constant, multiple, it's enough to get information about just the lengths of these, like the sequence of lengths of these sort of half-twists, right? The number of half-twists in each sort of in V1 through Vn. Right, so here this is like 1, 2, 3 or something. So if we can get some, so our goal now is to somehow relate the length of gamma and its self-intersection number to a sequence of lengths of V1 through Vn. And somehow, so this picture of like doing these half twists is sort of like the picture of these simple arcs on a surface. And so the way that these twists are going to interact is similar to how these simple arcs, or maybe combinations of them, will interact on the surface. Okay, so to get a bound on length, this might be sort of clear from the picture. Length grows roughly like the word length of this guy, right? And this is the only place actually on a pair of pants where constants are going to depend on the pair of pants. And then, okay, so intersection number, I'm going to simplify the picture a lot. So there are going to be some lies here. So we have this word. So for each of these sequence of half twists, we're going to assign a subarc of our geodesic that roughly winds around the same number of times, right? And then if you have like 2n half twists, you'd expect it to have this little arc to have n self-intersections, right? So somehow this guy, and then you have something more. If you have two of these guys and they wrap around the same boundary, they're going to interfere with one another, right? So if this guy winds around sort of, I don't know, 4 times, I guess, this guy runs around, or 4 half twists, this one has 2 half twists, then you can arrange them, only so much, but they still have to have these 2 self-intersections. You can arrange the guy with more self-intersections above the guy with fewer, so you get a minimum, but you still get sort of the same number of intersections as the smaller guy has half twists. Okay, so somehow this interaction between these twists is mirrored on the surface case, where you get some interaction between sort of sequences of simple arcs. Okay, so what you actually get is that the intersection number, you get bounds above and below of the intersection number of gamma with these word lengths.
What is the lower bound there?
So if you have n of these sort of twists in some geodesic gamma, then n squared gives you a lower bound for I of gamma gamma.
So each of these numbers. So
both of these separately, yeah.
Basically the max.
The max, yeah. Well, yeah. So, but you usually, when you actually do the thing, you use both of them in different places. Yeah. So that's right. It's the max. Okay. So you get some sort of, relationship between the length of these sort of twists and the intersection number. And then, okay, so for a pair of pants, what you do is that there's some restrictions on length of gamma and the intersection number of gamma, and they correspond to some restrictions on these words you get. And so an upper bound is an upper bound for words, and actually on a pair of pants, you can get a lower bound by constructing words in some specific way, right? Because you only have these 3 boundary components, so it's actually not so hard. Okay, so that's all I'm going to say about counting. I'm going to talk about sort of a related problem now, or something you can get from counting. Okay, so applications of counting. There's this theorem of Rivin series I'm going to talk about. So now G, without the C superscript, is going to be the set of complete geodesics on your surface S. Right. And then, so we sort of want an analog for guys with the most K self-intersections. But in fact, complete geodesics are going to have infinitely many generically self-intersections. So we want to sort of talk about the density of self-intersections on a complete geodesic. Right? So if K is some function of L, then we say G of K is a set of geodesics so that on each subarc of length L, you have at most K self-intersections. Right? Okay. K of L. Okay, so for K, yeah. Yeah?
So is it obvious that every complete geodesic will belong to G of K for some K? Or
yes. because you can't have more than roughly length squared self-intersections on a arc of length L. Yeah, or length squared. That's right. Yeah, so for instance, for k a constant, like for k0, right, these are just the complete geodesics of the most k self-intersections. Right, so this is a picture of something that is maybe part of a simple geodesic, complete simple geodesic. Right, just to illustrate that these guys also can be complicated. Wait, sorry? So to go back? What does that mean? Oh, sorry. It's a sort of a hero. There's a correspondence. So there's a, so there for like the length of a geodesic, there's a corresponding quantity you can take for the word, which is just like the sum of these. Oh, so no, for the surface case, you just sort of break it up into these simple arcs. And then you want to get something sort of similar to how we had this picture of these guys with self-intersections interfering with one another. So you can just choose a pair. So for the bound on a pair of pants, you can just choose a pair of pants. And so to get the upper bound, you don't really need to construct words. You could just consider all possible sequences of v1 through vn that have. No, so there are two different things. There's like a different way for counting on an arbitrary surface than there is for counting on a pair of pants. And then so are you asking why we went to a pair of pants? Oh, so the relationship is sort of, that's sort of a heuristic relationship. So the picture that really relates the two of them is that when you have some simple curve, let's say, and you have some guys that follow the same simple curve, then they must intersect one another. So on a pair of pants, you can sort of see this very clearly, right? And you get something similar on an arbitrary surface. So if you have some simple arc, right? Okay, so to count the number of simple arcs, you actually can't stop at simple arcs, which is why I didn't go into this. But if you take sort of your gamma and you write it as this sort of on a surface, you write it as some minimal collection of simple arcs, then any two of them put together are going to have an intersection, because I wrote this as a minimal collection of simple arcs. So somehow I get something equivalent to, I don't know, maybe somehow it goes like this, to curves with self-intersections on a surface. And then these curves with self-intersections sort of follow some simple closed geodesics in the same way as on a pair of pants you can follow simple closed geodesics. So then, two such guys that follow the same simple closed geodesic will interact with one another and will intersect each other. And so on a surface, the way you get the sort of bound for the number of simple arcs is you see, okay, how many of these simple arcs can I put down before they must start interfering with one another and intersecting? So that's sort of the picture for an arbitrary surface. But it really boils down to this, where you have something looping around a simple closed curve, and you have another guy looping around, and they intersect each other. And you sort of look for the same picture on an arbitrary surface. But then there's some more technical things where you have to you can't just take one, look at two simple arcs. You have to sort of start concatenating them and looking at sort of, actually it turns out you have to look at four tuples of these guys. And then they interact enough that you can bound how many of those four tuples you have. Was that more or less? Okay. Yeah. Yeah, so the thing is, on the surface, things are more complicated, which is why I stuck with that. Yeah. Okay. So back to applications. Right, so for one case constant, we have these complete geodesics with some constant number of self-intersections. And that's just an illustration that even simple complete geodesics can be quite complicated on the surface. They swirl around and just do endlessly. Okay, so, but what we want, well, the reason I made this complicated definition is we'll actually want, your average complete geodesic doesn't have finitely many self-intersections. We'll actually want to sort of give a function relation between the number of intersections and the arc lengths. Okay, so and then quick definition, if H is just some subset of the set of all complete geodesics, the image of H is just the points on your surface that H passes through. And then there's this famous theorem of permanent series that says if you fix the number of self-intersections, so if K is constant, then the image of the set of geodesics with the most K self-intersections is really small. It's nowhere dense in its Hausdorff dimension 1. Right? And this is in contrast to, I think that's probably the next slide. Right, this is in contrast to, like, on a finite volume surface, the set of closed geodesics, right, is dense, right? So it follows from mixing your geodesic flow and closing lemma. So let me show a picture, right? So on a once punctured torus, this is what you get. So these are like the first, I don't know, I stole this image from a paper of Bruiser and Parlier, and this is like the first, let's say 100? I keep changing the number in every talk. I think it's like, it's something on the order of 100. The first 100, let's say, closed geodesics.
And that one is G0?
And that one is G0. And you can see, really, these is a very thin set. You have these sort of bundles of thin guys, and they intersect each other, but each bundle is somehow very narrow. It's sort of like a Cantor set across an interval. Right, so that's sort of the picture that you get. Right, and then once again, we sort of want to interpolate between this, right? This guy is everywhere, and this guy is thin, and very, very small. And so you want to say for what functions, K of L, of like how frequently does the geodesic have to self-intersect, for it to start to really fill up the surface, or alternatively for how lazy does your geodesic have to be, right, for it to be nowhere dense and have Hausdorff dimension 1. So I'm going to do this on a pair of pants again, because they're easier, even though a similar result, I haven't quite worked it out, but a similar result should hold for an arbitrary surface. So let me I'm just going to go over the details of how you might do this. Oh yeah, so what do we mean by lazy geodesic? How industrious is your average geodesic? Right, so for almost any geodesic that you choose, if you look at arcs of length L, asymptotically, they'll have length squared times some constant self-intersections. Right, and then there's also an upper bound, like this. I guess actually I didn't give you a picture for why there should be an upper bound. So let me just draw that real quick. So the idea is that, what's the cartoon? If you look on your surface on a little piece, right, you're probably going to have, if you look at a piece of length L, you're probably going to have like L sticks going through here, right? And so how many self-intersections can L sticks have, right? So L sticks can have at most like L squared intersections, right? Of course, you have to make this precise, what happens when you cut off corners or something like this, but, right, so that's the cartoon for why we keep seeing this length squared showing up. Okay. So if you want your image of GOK to be small, then the growth, the number of self-intersections had better be smaller than length squared. Right. So here's what you get for a pair of pants. So you get, actually, on a pair of pants, you get on the nose that if your self-intersection number on these length L arcs is like even epsilon L squared, where epsilon is like small enough, then your Hausdorff dimension is going to be at most mu of epsilon, where mu of epsilon tends to 1 as epsilon goes to 0. Okay? So actually, there's some formula for mu of epsilon.
And do we know that mu of epsilon is bigger than 1 for epsilon?
Well, yeah, so there's a formula for it. But yeah, so the dimension has to be bigger than 1. Right. And then on a pair of pins, if you have self-intersection like little O of length squared, then the image of G of k is nowhere dense. Okay? Good. So I'm just going to give a quick rundown of this proof. So the idea is that we start with a combinatorial model for arcs, which is very similar to one we saw for closed curves, right? And then if two arcs have similar sort of words, then they must follow travel. So it's sort of like, you know, this is easier to see in the universal cover. You know, if you have sort of similar, you know, some pattern of following boundaries, then you have these two arcs. They must, you know, these two arcs must sort of stay close to this sort of zigzaggy thing where you just follow around the boundaries. And so in the, you know, so they must follow travel. In particular, in the middle, they must come close together. So each word that you can get for an arc corresponds to lots of little sticks going through, you know, some like pretty small rectangle, right? And then the number of these words are going to give you the number of these sort of bundles of sticks. And you sort of balance, you know, the number of words against sort of the, you know, the growth. You look at the growth of the number of words as length grows, and the number of words depends on intersection number, so you somehow get a, you know, bounds on Hausdorff dimension and sort of density. Yeah.
So I'm supposed to be using a previous result?
Yes, you do use the counting result. So the number of words is sort of translates from closed curves to arcs directly. Yeah, so you can count the number of sort of these patterns in sort of the same way. Right, and then you get something like these thin sets. Okay. So I'm going to end there. Just a bit early.